So good day everyone once again, my dear people. It is yours truly, Jasper Tom Isiderio of PSEC3A, and today I'm going to discuss to you about transmission lines, open or short close. So okay, let's try to do this. So what is a transmission line? A transmission line is a conductor or conductors designed to carry electricity or an electrical signal over large distances with minimum losses and distortion. So transmission lines can be your LAN cables or their Ethernet cables connected in your laptops or computers. It can be your antennas that's connected from your TVs, of course your antenna up on your rooftops, and many more, as long as it carries your electricity or your electrical signals. Okay. So input impedance of the line length, or zeta, terminated in impedance, ZL. Z is actually the symbol used to depict impedances. So impedance is actually the effective resistance of all electric circuit or components to alternating current arising from the combined effects of ohmic resistance and reactance. This means that our impedance is actually just used, or is termed in your AC or your alternating current. So it is the combined or the combination of your resistance and your reactance. So in your DC, you just use your resistance. So this is the formula right here. Right here is the formula to get the line length, impedance of the line length at a certain length. So zeta is this is the value. It's the value of a length. It can be in meters, but usually used in meters in standard. So it is equal to your ZO, or characteristic impedance, multiplied by the quantity ZL, or of course your terminated impedance, plus JZO, tangent of beta, or your phase constant times zeta. This right here, as you can see, these have the letter G. It means that this is a complex number. It has this ZL is the real part, and this ZO tangent B is the imaginary part. We can depict this, or we can say that this is the imaginary part because this have the J right here. It can be written as J or I in some other books. So it's all divided by your ZO, or your characteristic impedance, plus your J ZL tangent of beta plus multiplied by zeta. So that's your general formula. So next is the phase constant. We will discuss that because of course we will use that in our formula. It's good that you know that too. So this is the imaginary part of the propagation constant, measured in rad or radians per meter or degree per meter, but preferably radians per meter, because as you can see the note, all angles should be in radians, and beta right here is an angle multiplied by r zeta. Means that it should be in radians per meter. So phase constant formula, these have various formulas, but I think right in the next I'm gonna show you some problems that we will solve for a bit, and let's see what we're gonna use. So first formula is 2 pi over your wavelength. This right here is a symbol for your wavelength. So another formula is your 2 pi multiplied by your frequency divided by your phase velocity. Or you can also use 2 pi multiplied by the frequency multiplied by the square root of your absolute permeability of the line and the absolute permittivity of the line. So these three can be used to get your phase constant formula. So if you recall the velocity formula, this right here, VF, is velocity factor formula, or velocity factor only, is equal to your velocity, your phase velocity divided by the speed of light. And our ZL, or zeta impedance of your zeta formula, is equal to this. Okay, so this one is we're gonna use it later for our problem. So because we have here in our beta have our VP right here. Since it's usually commonly used, it's much easier. Okay, so this is the input impedance of a shorted line. If lines are connected together, it's shorted. So we assume in shorted line that our ZL is equal to 0. It means that this ZL right here is 0, and this ZL right here is also 0. That means that this will cancel out. This will cancel out. It will be 0 plus 0, 0 plus J0 tangent of beta zeta. So this 0 right here will go up and will cancel out this 0 in the bottom. Plus, so what will remain is this 1 plus 0 tangent beta zeta, as you can see right here. Same goes for the input impedance of an open line having the infinite resistance. So if we substitute this infinite or infinity in our ZL in our main formula, we will get this as a simplified form. So this is what we will use in our open line transmission line to get the input impedance. Okay, so this is our sample problem. Never mind this 0.50 ohms because I have already given this sample right here. So a 200 ohm open line has a velocity factor of 0.76 at 5.7 gigahertz. So we should find the phase constant and the Z input at 15 meters. So Z in or our ZL at 15 meters. Okay, so as you can see right here, never mind this. This is what it looks like for the open line. As you can see, this right here is not connected to anything. It means that it's open and it have a infinite resistance because just nothing can pass it, so it's very resistive. So we will go to my already solved formula or already solved solution for this problem, and I will discuss it to you. So right here, as you can see, this is the formula for our open line, formula for our beta, formula for our velocity factor. So our given is velocity factor. Right here, as you can see, velocity factor is 0.76. Our ZO is at 200 ohms. And our frequency is at 5.7 gigahertz. And the zeta is at 15 meters right here. So first, the thing that we will do is we will compute for our velocity, phase velocity, so that we can get our beta. So as you can see, phase velocity, since VF is actually equal to the phase velocity over the speed of light, so we can just multiply speed of light on both sides and we can now get the value of our phase velocity. So phase velocity is equal to your velocity factor multiplied by your speed of light. It means that this is 0.76 multiplied by 3 times 10 raised to 8. That's equal to your this right here. This 2.28 times 10 raised to 8. So next is, after we have your VP, we will now solve for your beta. This is equal to your 2 pi f over VP. Since we have value of our VP and value of our f, we can solve for our phase constant. Okay, so we just input this in calculator. Of course, should be in radians mode because it's stated in the notes earlier that we should always use it in radians. Okay, so this is the value that we get after inputting it in the calculator, 50 pi or 157.0796, and it goes on, so I just rounded it up. So after we get our beta, we now solve for our Z at 15 meters. So we just input this formula and we just substitute it. So it's actually tangent of 50 pi plus multiplied by 15 is actually 0, and any number divided by 0 is infinity, and any number multiplied to infinity is infinity. So this answer is infinity. It means that our line is actually not letting in or out any power. So it's just technically off. It's not working. So it's just open. Okay, so next is we have a second problem actually. So as you can see right here, our beta is 157.70796 and our z at 15 meters is actually infinity. Next is of course the shorted line. Of course, shorted line, it's connected together. Never mind, of course, your ZO, because I've already given a ZO of 200. So a 200 ohm short circuit line has a velocity factor of 0.86 at 5.7 gigahertz. So let's find the phase constant and the Z at 10 meters. So let's go to my solutions right here real quick. So as you can see, this is the formula for our shorted line, beta of course, and our velocity factor. Same process as the earlier. We'll solve for the phase velocity using the formula for your velocity factor, and after that, of course, 0.86 multiplied by the speed of light, 3 times 10 raised to 8, we got 2.58 times 10 raised to 8. That's a big number. So beta is actually 2 pi f, and Vp, of course, your velocity, phase velocity. So the answer that we got from that is 138.814559. This is the exact value that I got in the calculator. That's all it can display. So I just stored it in a variable and inputted it once again to solve for our impedance at 10 meters. So plus j ZO tangent of beta zeta is actually 200. Multiply that to tangent of 138.82 multiplied by 10. So we got negative J93.756 ohms, which means that this is a capacitive. This is a capacitive impedance. Okay, so go back to our main problem right here. As you can see, right here is just this. Okay, so pretty simple, pretty easy. I hope you find use for it, and if you're solving for something or you use it for school or whatever. So your tutor right here, signing off.